Good morning, everybody. Yesterday we started talking about the processes and threads. We did a small introduction. Let's continue our discussion about processes. We said that process is the first abstraction. I wonder what this is. I think, yeah. Okay, I'm going to ignore it. We said.
Sir, can I have a question before beginning?
Sure.
We talked about operating system handles processes, keeping process stable and track of the process. And we talked about if a process waiting a data, it going sleep until the data is ready, it sleeps. But let's assume we have two programs at the same time running, and both of them waiting for mouse click. How the operating system knows the mouse click data, which one processes data waiting?
Well, I mean, with the mouse clicks, it's a matter of how you design your graphical user interface. Okay, with the Windows environment, you have this concept of focus windows. Okay, so currently my focus window is this window, this active window, because I know that it is highlighted, right? I mean, here it says that your whatever you are going to type is going to go in there. Okay, if I have two windows, let's say I have a window here and I have, let me,
cannot see your screen.
oh, I didn't turn my sharing on. Okay, do you see it now?
Yes.
Yeah.
Okay.
Yeah, we do.
And another window like that. Okay, now both of them are waiting for keyboard entries, right? This one or that one.
Yes.
So whoever has the focus will get the characters, or whoever has the focus will get the. I mean, when I make a click here, okay, when I make a click here, the operating system knows at what position the mouse is. Whoever has the focus, okay. So operating system communicates that information to that window only. So it is not a decision of the operating system. It is a decision of the graphical user interface designer's decision, right? So most of those kind of questions can be answered by looking at the graphical user interfaces. If I change your question a little bit, just a little bit, let's say there are two processes waiting for data from the disk. How does the operating system know which process is going to get the data from the disk? Okay, I think a similar question was asked before. The disk is a serial mechanical device. Okay, it can handle only one thing at a time. So if two processes are waiting for this data, they have requests, right? They say that read me this track. The other one says that read the other track. Okay, so operating system keeps these requests in a queue. So first in, first served. Okay, first come, first served fashion. If I am doing that, an operating system does the resource sharing in that way. So most of the time it is the operating system's responsibility to make these arrangements if the device can respond only once. Mouse cannot be shared between two processes, so one of them has to have the data, mouse data, such as the clicks or the double clicks or the selection stuff. But the graphical user interface designer usually makes that decision.
I have one more question.
Sure.
Let's assume we listen music from computer, and at the same time we are talking with some friends with Skype or whatever. The output of the two program is the same, and the sounds overlapping, but we know that a processor can handle long process at the same time. How does it happen?
Well, it is the task of the sound card in this case. Previously, in the first days of the days, okay, a sound card could have respond to only one request at a time. So you can either play something or record something and don't do anything else. Nowadays, the sound cards can be used by more than one process. Okay, so virtually there are many sound cards there, and operating system is responsible for assigning. Let's say, I mean, it is like many cores of the same CPU, right? You have many sound cards, okay, and many processes can use each of them. Let's say virtually I have 16 different channels, sound channels. So it is the task of the operating system to assign those channels to the processes. If I need more than 16 channels, then operating system is going to tell you that no, that's enough. I cannot give you this many sound channels. So it is the capability of the sound card that can respond to more than one request at the same time. If I use the old sound cards, very old sound cards like from 1990s, then it wasn't possible. It wasn't possible at all. I mean, if somebody's using your sound card, then they are using it. Nobody else can use it. It is either playing something, recording something. You cannot play it at the same time. So it is, again, it is operating system to manage the resource of the sound card. Okay, how many channels do I have? 16 channels. So if there is a 17th process trying to use the sound card again, it wants a new channel, operating system is going to say no. Okay?
Okay.
So all the questions that you are asking, Murat, is about how does the operating system manage these resources. Okay, if the resource is limited, I have only one sound card, one sound channel, operating system cannot do anything. Okay, you are going to, and sound channels actually they cannot be time multiplexed. Either one process uses or the other one uses. You cannot go back and forth for a single sound channel. In that, if I do that, both of the sounds will be messed up. It's like the same thing with the disk access. The disk, the hard drive, okay, it's a mechanical thing. I can read only one thing at a time. I cannot read two things, so I cannot serve two processes at the same time. So who's going to get the disk? So it is operating system's decision again. And we are going to spend maybe half an hour to look at the algorithms to make these arrangements. Should I do first in, first out? Should I do more higher priority task first? Or should I do whoever can be responded in a more efficient way? For example, if my read write head is at the beginning of the track, and if the other process is asking me a data that is very close by, I can answer that one before the others, etc. So those are all design decisions. Those are all disk request, execution decisions, and we are going to talk about them. For now, we are going to talk about how do we satisfy the request of the processes in terms of CPU. All the processes, they need the CPU, okay? So how should I manage these resources, the CPU resources? And most of the time in this chapter, we are going to assume there is only one CPU available. So most of the questions that you are asking can be posed with respect to the CPUs. I mean, if three processes need the CPU, who's going to get it first? Okay, something like that. So process is the basic abstraction of the operating systems, and all the operating systems, okay, they start doing this abstraction, and historically it is the same thing. They did the same thing. Let's say they said that, okay, let's try to abstract the complications of the process creation on multi-programming from the user, so that everybody would think that, all the processes would think that they have their own CPU available. Some computers, for example, the early computers, 1950s, they couldn't make this abstraction because the computers were very, very weak. They were not powerful enough. So they didn't have a very strong abstraction of a process. Okay, they say that, okay, there is only one process running. Okay, so all the registers, all the stack pointers, program status word, memory, everything, it belongs to that program. Whatever they want it. Okay, so the operating systems are not there. They are using this very simple process mechanism, and there is no abstraction at all. We did the same thing with the 1980s with the personal computers. With the personal computers, okay, you could run only one program at a time, okay, and that's it. There is only one operating system, okay, and one program. The program takes control, and usually it runs as much as it likes, okay, and it is possible that it runs in an infinite loop and it doesn't come back. Operating system cannot do anything at all. So if a program takes the CPU and if it is in an infinite loop, all you can do with this kind of computer is to turn off the power. That's it. You cannot stop that program at all. Okay, and because there is no hardware hub, and there is only one program can run at the same time. There is no multi programming because that's my hardware. My hardware allows only that much. But nowadays we don't do that, okay? We have lots of hardware help, okay? We have interrupts. If a program runs too long, there is the timer interrupt, it occurs and the operating system takes the control. Okay, so processes are oldest and most important abstractions. That's why whatever structure of operating system you have, at the bottom level, you have the process scheduling, okay, and process supervision, creation of the processes, scheduling of the processes, etc. Okay, that's why this is the chapter number 2. We start abstracting the hardware with the abstraction of the CPU. I think I showed you this before. So one common mistake that the newcomers to the operating system world make is that the process switching happens and they would assume that it happens automatically. I mean, the process switching happens, of course, but it doesn't happen automatically. The process switching is done by the operating system. So when I switch from, I think I did this last time, when I switch from process 2 to process 1 here, the switching is done by the operating system. Okay, so what happened here to cause the switch? Two things might have happened. One is timer interrupt. Okay, timer interrupt happened. Okay, when the timer interrupt happened, operating system handled the timer interrupt, and the operating system decided that process to use the CPU long enough. So it will make a decision. Who is going to use the CPU now? Process number 1 or process number 3? Okay, so so it made a decision. It's going to be process number 1. Here, when timer interrupt happened at this green circle, when timer interrupt happened, okay, operating system cannot find anybody to use the CPU because all of them are blocked. Well, then in this case, this process 1 is not stopped because of the timer interrupt. If it is stopped because of the timer interrupt, operating system would have said that, okay, you continue like that. So that means that process 1 wanted to get some data from the disk or from the network or from somewhere else. Okay, so it is blocked. Process 2 and process 3 should be doing the same thing. They are waiting for something to happen. Okay, so this time here, this time slot, maybe 100 milliseconds, the CPU sits idle, doesn't do anything useful. CPU sits idle, doesn't do anything useful. Okay, after the data is available now, okay, the operating system knows it, and process 2 can now start because the data for the process 2 is ready. Okay, again, what happened here? How did the operating system know that the data is ready? It know about it because there is an interrupt. For example, a hard disk controller caused an interrupt saying that whatever you ask me, it is ready now. So operating system handled the interrupt, transferred all the data from the controller's buffer to the memory, and operating system realized that by looking at the tables, process 2 is waiting for that data. And it wakes up the process 2, and process 2 can now continue.
Sir,
Yes.
do we assume that during the context switching between one process to the other, do we assume that the operating system itself doesn't take any time to work itself?
No, no, no. Of course, operating system is a piece of code, remember? If you are a piece of software, then you have to use the CPU. Definitely, operating system is wasting some time, some valuable CPU time.
But but in the context of context switching, we say like, okay, it's 1, then it was idle, then it was 2, then it's 1 again. But like the operating system side seems like very empty. That's why I was wondering. Do you assume that it's always like that?
I did not exactly understand your question, but the rule is whenever operating system is using the CPU, most of the time other processes are waiting for the operating system to finish up its job. Okay? Operating system is like a process. Privileged process, but it's a process. Whenever it uses the CPU, it is using a resource. Okay? So the switching is not free. Okay? Context switching, when we say context switching is expensive, it is expensive because it is taking lots of CPU time. Okay?
Which is done by the operating system.
Most of the time, yeah, it is done by the operating system. Sometimes some part of the context switching is done by the hardware, but again, it takes some time.
I see. All right, thanks.
Okay, this analogy is very good. Operating systems are like governments. Okay, the intentions of government are very nice. They are there for the people. So, but the governments, they need resources too, right? I mean, you need to pay the government workers. I am a government worker. You need to pay me, okay? But why is the government is paying me? Because I am providing education and research. Without people doing education and research, okay, everybody knows that there is no technology. Nobody is going to produce technology. Nobody is going to produce new engineers, okay? So government or the people has to spend some of their money for the universities and schools and the health system and the communication system and the transportation system and etc. But if the government is too big, okay, everybody is working for the government, everybody is a teacher, everybody is a police officer, everybody is a politician. So who's going to produce stuff? Who's going to produce the goods? Who's going to make cars? Who's going to give who's going to do the barbershop stuff, produce the clothes and etc. Right? So governments cannot be too big, but if you drop the government size to zero, then there will be anarchy, right? There is no health system, there is no protection from the unlawfulness and that kind of stuff. So operating systems definitely need resources, disk resources, CPU resources, memory resources, okay? But its intention is good. Its intention to be useful.
I see. Thanks.
Okay, good. So again, usually this is important. A process is just an instance of executing program. When we write and compile our programs and link it, an executable code is created and it sits on disk. Okay, we call that a program, right? That's a program to be run. But when it starts running, okay, when it starts running, now we talk about the processes. A process is a running program, okay? A process running program. What is the difference between a running program and a program that is sitting on a disk? Of course, with the running program, you have the state, okay? You have the program counter register. You have all the registers that is used by the program itself. you have your memory configuration, you have your open files, okay, you have your network connection, etc. All of them put together makes a process. All of them put together makes a process. And at the same time, you can have more than one process in your memory. Okay, that doesn't mean that these four processes are running at the same time, because it is not possible. There is a single CPU, that's our assumption, and only one process can use the CPU at the same time. But virtually for a user, it looks like there are four programs running at the same time. Okay, it looks like there are four programs running at the same time. For me, my Teams program is running now. Okay, my PDF viewer program is running, the second one. Also, I am recording this lecture using the OBS recorder. That's the third one. Also, I think I have opened my web browser too. That's running too. So for me, I feel that all of these programs are running at the same time because I am doing four different things. But in fact, assuming that I have a single CPU, in fact, what is happening is my CPU keeps switching back and forth between these processes. Okay, so it runs A little bit, then B, then C, then D. Okay, the switching point, the cause for the switching point is sometimes process A needs help from the operating system. So operating system gets the control, and to provide that help, it needs more time. So it says to A that, okay, you need to wait for a while, and I will let you know. Okay, process A actually doesn't know that it is waiting. Okay, all the process A knows that it needs data from the disk, and it is waiting for the data. It doesn't know that it is on hold. Okay, it doesn't know that. That's why as programmers, when we say read some file from the disk, when we issue that read function, when we call that read function, we assume that the data will be available and I will get the data. That's it. We don't know that we are going to wait for a while. Okay, that's the abstraction of the process. Okay, we don't know that when we say read, some other process can get the CPU. We don't care. Okay, if you are knowledgeable, maybe you would know, but you don't care. You write your program like a sequential program, and that's it. Okay, so conceptually, each process, each running program has its own virtual CPU. Okay, because of the abstraction of the CPU done by the operating system. And similarly, conceptually, each process has its own address space on memory. Okay, the process says that I have my address space, and I am using that address space freely from address number 0 to some large number. Okay, but in reality, there is lots of switching happening. So this is in reality, but this is what we feel. We feel that all of those programs are running at the same time. In this chapter, we are going to assume that there is only one CPU available, but we know that in practice, even the simplest computers, they have more than one core available. Okay, they have one more than CPU available. What is the difference between multi-core and multi-CPU computers? What is the difference? Multi-core and multi-CPU.
Multi-core consists cores in one physical processing unit, and multi-CPU is two different or three different, four different physical units.
Exactly, yes. This is your CPU, physical CPU. If you have more than one CPU on the same system, two CPUs, complete CPUs on it, okay? No problem. So if this one can run a program, this one can run another program at the same time. But with the multi-core systems, there is the CPU core replicated. Two of them are available. Each one can run a different program at the same time. But they have to share, okay, at least there's level 2 cache, okay? and they have to share the communication mechanism between this CPU and the memory. Okay, they have to share this bus. Okay, so producing multi-core CPUs is cheaper than putting two CPUs on the same computer system. So, but for us, we don't care about them much as programmers. If we are writing our code, we don't care if it is running on a separate CPU or in a core on a different CPU. It is the task of the operating system to manage all these resources. Should I run this program on this core of this CPU or another CPU? Okay, it is the task of the operating system. I don't. As a programmer, I don't care. I don't want to know. That's too complicated for me. Okay, so it is CPU management. This is possible because of the idea of the processes and threads. Good?
Sir,
Yes.
can I tell the operating system to not switch another process? So something like, for example, I'm doing something critical right now,
Yeah.
and do not switch to another process. Is this possible?
No. As a regular process, you cannot prevent. You are saying that I am going to disable the interrupts. That's what you are saying. Don't interrupt me. I am going to disable the interrupts. And if this causes an interrupt, ignore it. If timer interrupt goes on, ignore it. Right? That's what you are saying. As a regular program, no, you cannot do that. If you like to do that, then you need to disable the interrupts, and disabling interrupts is a privileged instruction. Privileged instructions can be executed only in the kernel mode, and you need to be very, very careful about it. I cannot trust a regular program to disable the interrupts, because what happens if the program disables the interrupts and crashes? Okay, that's going to take down all the computer. I cannot let you do that, even if you have good intentions. And think about a program with the bad intentions. It's a virus. Okay, it is disabling the interrupt, so the whole computer is paralyzed. That's not a good thing. But there are ways of understanding if an interrupt has occurred. You might say that, okay, I am doing something important, and if an interrupt occurred and I lost the CPU control, when the control comes to me, there is a way of understanding it. So if there is a damage done, you can understand how much damage you got. If you are doing something time critical, okay, if you are doing something time critical and it is very, very important, maybe you should be using a real-time operating system. With the real-time operating system, you are guaranteed to get your results in a given amount of time. It is guaranteed by the operating system. Okay? Because all you are doing is something important. But if you are doing like semi-important stuff, like every 20 milliseconds I have to show a frame to the user because I am a video player. Every 20 milliseconds I need to show this frame. Okay, that's important. But once in a while, it is okay if I don't show it. So the user will see some kind of a flickering. That's it. That can be tolerated. That's possible with the everyday operating system like Windows or Linux.
Okay, thank you.
Okay, good. Let's look at this process creation stuff. When do we create new processes? Okay, first, when the system is initialized. Okay, when the system is initialized, there are many processes created, and they wait for something to happen. These are called daemons. They just wait. For example, your email server, web-based server, printing server, network server, etc. Okay, they just wait for something to happen. And remember, I showed you my process table. Okay, all the processes are listed here, and I think we counted up to like 200 of them, right? So these are all service processes, okay? Some kind of a server, okay? Some kind of a plug and play server, some kind of a network server. I don't know what this is. Phone, it says. I don't know what it is. Well, this is a very generic operating system, so maybe there is a phone services happening, and it looks like it doesn't use any CPU. Very small amount of memory is used, and never use any power. Okay, I guess that's it. So one of the reasons why we create processes is at the initialization. These kind of daemons are created, and they are blocked, and they are waiting. They are waiting for something to happen. So when would they start running again? An interrupt has to happen. For example, that TCP/IP server, something I received I received some data from the over the network. Okay, it caused an interrupt. An interrupt is handled, and the data is ready now. Who is waiting for that data? That TCP/IP server is waiting for that data. So CPU, the operating system says that, okay, this process is now ready to run. Okay, now that process can run. So they are all waiting there, and they are, of course, remember that although they are not using much CPU because they are blocked, but they are definitely using some memory, and memory is resource, very valuable resource. Okay, another process creation option is a process creating another process. Remember, for Unix, it is fork. If you make a system call fork, you are creating another process. Okay, some users, when the user says that I like you to run this program for me, then that's another process creation example. Of course, this one is going to use fork again. Okay, because this shell is just a program doing another one. Rarely, not for our operating systems. Okay, because we don't use our Windows operating system or the Linux operating systems for batch jobs. Okay, but for the batch jobs to start, they need to be started, then a process has to happen. Okay, so important thing here is that at the system initialization, lots of processes are started, then processes are started by the users, or processes are started by the programs themselves. Okay, we talked about it. For the Unix, fork is the way to create a new process. It's a system call. Okay, after the fork, okay, I have two exact copies of the same process. So one is a parent, the other one is a child. Usually the child process executes one of these system calls, execve, with environment variables and the parameters, or similar. So it changes its memory image. Usually says that, okay, I don't want to be like my parent anymore. I'm changing my core image with the core image of the this program on the desk. Okay, so the same thing with the create process of Windows. Create process, of course, it creates a process and it loads a program from the desk. So it is doing fork plus execve, as we have seen previously. And Windows 32 has about 100 other functions for managing and synchronizing processes and related topics. POSIX doesn't have that many because, as you know, POSIX has only about 100 procedure calls, system procedure calls. Okay, good. Process termination. When does the process terminate? Voluntarily. When your program is done, you call exit. Okay. When the program is done, you call exit. and usually you would give an exit code. We would give 0. If there is no problem, we would give -1, -2, whatever the number, if it is a voluntarily exit but with an error code. Okay, and exit process in Windows is the system call to terminate voluntarily a process. This one and 2 is the same thing. You are terminating your process with a normal way or the error way. Other than that, your process might be terminated involuntarily, okay, if a fatal error occurred. For example, what would be a fatal error? You executed an illegal instruction. Depending on the operating system design, sometimes operating systems tells the hardware that if a user executes an illegal instruction, just ignore it. But some operating system tells the hardware that if a process executes a illegal instruction, okay, just terminate it. Okay, for example, trying to refer to non-existent memory location, okay, or dividing by 0. These are illegal instructions, illegal memory locations. Sometimes we call them segmentation faults, right? So these are the fatal errors. Or sometimes operating system may decide to kill the process. Okay, so if I am privileged, I can send the kill signal to a process, and that process is killed if I have the privilege, if I have the permissions. Okay, so processes are ready to accept signals. If I send the signal number 9 to a process, that process will be killed. Okay, so again, it's involuntarily somebody else is killing the process, and I could do the same thing on Windows too. What do? I would go there and take one of the processes here. Okay, see, it says that it is suspended. Okay, and if I like, I can just terminate this process because I have the permission to terminate it. That was my process. Okay, good. So that's the process termination. We looked at the process creation and we look at the process termination. Some operating systems have this structure, okay? There is process hierarchies. Okay, remember the only way to create a process in Unix is fork. Whenever you do a fork, you have the 2 copies of the same process, but one of them is parent, the other one is child. So there is always this parent-child relationship between the processes. So when Unix starts, there is a special process called init, initialization process. Okay, that process is the parent of all the processes in a Unix system. Okay, so if init is killed, then all the processes on a Unix system is going to be killed. Of course, to kill init, you need to have enough permissions. In Windows, we don't have parent-child relationship supported directly by the kernel. Okay, you may see some configurations in Windows processes. It might say that there is a parent-child relationship between the processes, but this relationship is not directly supported by the kernel. It is supported by some extra bookkeeping done by the operating system, but not by the kernel. But Windows doesn't support the child process hierarchy mechanism directly by the kernel. Okay, it is how it is designed. Okay, so let's look at the life of a process actually. Process states. Okay, let's look at this command. I like to cat I like to see the contents of chapter 1, chapter 2, and chapter 3 documents on my current directory. Okay, so if I am typing this command by itself, I would see them on my screen, but I am piping them through this grep command. So I am searching for the word tree. I am searching for the word tree. When I find it, I will print them on the screen. So that means that this cat command and the grep command are going to run at the same time. This one is going to produce data. This one is going to consume that data. If cat is fast enough to produce all the data, this would run, and if it is over, then grep start would start working. But cat is not that fast because it needs to read the disk, and it needs to read all the lines, and it needs to put them to the standard output. And grep is running too, so grep needs the data from cat. So grep is blocked at the beginning. Cat is running. When cat needs data from the disk, it will be blocked. So both of them are blocked. Okay, so that means that sometimes both of them are blocked. Sometimes cat is running. Sometimes grep is running. But two of them are not running at the same time. Never. They never run at the same time because I have only a single CPU. Okay, so keeping this in mind, let's look at this table. We say that the processes could be in 3 different states. A process could be running, that is, it is using the CPU. Okay, it is using the CPU. So it is continuously changing the program counter. It is executing its instructions on the CPU, and running the instructions, executing the instruction on the CPU means that changing the register and everything, and it is a running state. And then if I am not running, I could be either in ready state or the block state. Ready state is this: I am ready to run. I need all the data that I need, but I don't have the CPU. Okay, so why would a state be in a ready? Why would a process be in a ready state? It is because somebody else is using the CPU. So it could happen, right? Many processes are ready to use the CPU, but somebody else is using the CPU because I have only one CPU. Okay? We don't want many processes to be in the ready state. Okay? Question: how many processes can be in running state on a single CPU computer?
Only one.
Only one, just one. Okay, that's good. How about ready state? How many processes could be in the ready state?
Several.
Several. Okay, including 0, right? Including 0. Okay, so running could be one, just one. It is not 0. Okay, because CPU cannot stay idle. When we say CPU is idle, CPU idle means that operating system is using it, but operating system is running some kind of a stupid loop maybe. Okay, so CPU cannot be idle. It is doing something. Maybe it is executing no op instruction, no operation instruction. So exactly one process that may include the operating system is running. 0, 1, 2, 3, 4, 5, any number of processes could be in the ready state. And block means that I need to run, but I cannot use the CPU because I need data. I need some kind of a data from somebody, either from a device or from some other process. Remember, this grep is blocked because it needs data from this process. So it is waiting for this process. So when a process is blocked, it is blocked because it needs data. Okay, it needs data from some other process, some device, or sometimes it is blocked because it says that, okay, I'm going to sleep for 200 milliseconds. Why would you sleep for 200 milliseconds? This means sleep 200. Why would you sleep for 200 milliseconds? Why would you write such a program?
To be sure the process is done.
What do you mean done? To be sure that somebody else is doing something and I am letting them have enough time.
Yes, yes.
Well, that would be a very bad assumption, though. I mean, if 200 milliseconds is not enough for them, because there is no guarantee that there's not a real-time operating system. It could take 10 milliseconds or sometimes 2 seconds.
Maybe due to the human factor of the program.
What do you mean?
Maybe,
Yeah, explain it a little bit.
let's say, for instance, a program runs in 10 milliseconds. It only needs 10 milliseconds to run, but a human cannot comprehend that 10 milliseconds,
Yeah,
and it needs to happen in 10 normal seconds. So we put sleep 10 seconds so
yeah,
that it
yeah.
always run in 10 seconds.
Yeah, you exactly described what a video player does actually. I cannot show 1,000 frames per second to a user. That doesn't make any sense. The user cannot see 1,000 frames per second. That would be overkill. So at most I can show maybe 60 frames per second, right? So that means that after each time I show the frame to the user, I need to wait. I need to wait 1 over 60 seconds so that I can show my new frame, right? Because of the human factors. Okay, because of some human factors. Or maybe I am updating something on the screen. Okay, some kind of a display. So sometimes I am blocked because I issued such a system call. I asked the operating system to suspend me for 200 milliseconds. Okay, I am blocked in that case. Okay, so I'm going to show you very important. It looks very simple, but it is very important. If you understand this picture, you are very well understood what a process is actually. So a process could be running, ready, or blocked. Let's look at this one. Or maybe I should take 10 minutes of break. After the break, we will come back and we will talk about when does this number 1 happen, when does this number 3 happens, number 2, number 4, and I'm going to ask you why there is no number 5, why there is no number 6. Okay, number 5 and number 6 should not be there, but well, it is not there. But I'm going to ask you why there is no number 6, why there is no number 5. Okay, so let's take 10 minutes of break. We will start at 12:31. Okay, so process state transition figure, nice figure. Let's look at these and let's try to see what's happening. Okay, so if my process is running, I could be blocked. Okay, by following this transition, I could be blocked. Okay, tell me the reason for number one. Why should I be blocked?
Reading the data from hard disk, for example.
Yeah, I asked the operating system. I made an operating system call. Okay, system call, and I asked some data from the hard disk, from the network, from the keyboard. Okay, and operating system said that okay, that data is going to take some while to be ready, so I am going to put you in block state. So there is a system call definitely. This process is a system call, and I am in blocked state. Also, I may say okay, sleep 200 milliseconds. Okay, again I am blocked for 200 milliseconds. So in order for this one to happen, this running process has to make some kind of a operating system call, right? Operating system call. How about number two? How can I go from running state to ready state? Ready means that, okay, I am ready to run. Everything is ready. I can use the CPU. So how come I can go from running to ready?
Time interruptions. Yeah.
Yeah, I got maybe a timer interrupt happened. When timer interrupt happened, operating system said that this process has used the CPU too much, so I am going to put in a ready queue. There is a ready queue. Okay, there is a ready queue. I am going to put that in ready queue, and I will let some other body, some other people, some other process, sorry, some other process to I will let some other process use the CPU now. So that's number three. So there is a ready queue. There is a ready queue, like the queue. In this queue, first in, first out, maybe. Sometimes it is not. I mean, but it changes from time to time. Process 1, process 7, process 2, process 3, etc. Okay, so it takes one process from this ready queue, the scheduler, and it makes it running. Okay, so that's number 3. How about number 4? How could I be in how could I be in number 4? What would cause this transition from block to ready?
My data is ready.
Your data is ready. How do I know that the data is ready? I am in block state. I am waiting for something to happen, right? I am waiting for this data to become available, or I am waiting for keyboard stroke to be available, or I am waiting for some other thing to be available. Okay, so if that thing is available, operating system would know. Then operating system will take me from the block state to the ready state. Okay, so it is the operating system always doing these transitions. Operating system says that okay, you made a system call, I'm going to put you in blocked state. Okay, the timer happened. Operating system says that you use the CPU too much. There are other people waiting for the CPU, so I am going to put you in the ready queue. And operating system say that okay, you are in the ready queue, and your time is now. Now you are going to use a CPU again from block to ready. Again, you will be in the ready queue now. You are not blocked anymore. So all the transitions are done by the operating system, and the book says this. Okay, these are the stuff. So one, process blocks for input. Two, scheduler picks. Scheduler is the operating system part that decides who is going to use the CPU. Okay. Two, process picks another process. Okay. Three, process picks this process to run. And four, input becomes available. So these are the transitions between the states of a CPU. And I think I found this from some other source on the web. I don't remember. It is doing the same thing. I think just on each arrow they put these transition events. They say that there are two more states, created state and the terminated state. Well, I mean, it depends who is talking, okay? We usually don't see these states. Okay, it is ready, running, and waiting, blocked. Okay. Scheduler, dispatch, interrupt. So this one says that interrupt happened. It's good. So running is IO or event wait. Running to waiting. Okay, this is good. So know this transition diagram very well and try to understand it. And as I said before, let's look at this arrow. Why there is no arrow between block to running?
Because it is not certain that this process is already ready for the run. It may be an operator state, maybe.
Well, I mean, couldn't it be that the data is available now you can run? The data is ready and now you can run.
But it should first put in the queue, then it will run, I think. The operating system will put the process in the ready queue and it will start running again.
Mm-hmm. Because this number 3 is only handled by the scheduler. Scheduler checks the ready queue and it picks one appropriate process to be running. Okay, so the scheduler doesn't look at the block processes and if the data is running, so it doesn't work that way. So some part of the operating system makes that block process ready and the scheduler picks the appropriate one, because the scheduling is very important, process scheduling, and we are going to look at it. There are many algorithms for the scheduling. I need to pay attention to how much that process has used the CPU, what is the priority, okay, and process hierarchies and etc., interactivity and etc. Okay, so I need to be in the ready queue first. That's why there is no arrow from here to here. How about that one? Why there is no arrow between ready to blocked? Remember number 1.
Why should be so?
Why should be is not a good question. I mean, I could ask that question as an instructor myself, but why should be is not a good, why not is not a good answer for a student, okay?
It doesn't seem meaningful to transition ready to block. In that case, I can ask why I became a ready mode.
I think block status is for processing the running, but operating system says interrupt this. If some process is in ready state and it is not running, it doesn't make sense to interrupt them.
Ready, exactly, Murat. Ready means that it is ready to run. Everything is available. Only the CPU is missing. Okay, but the process is not running. How can a process go to block state if it is not running? Okay, what was the reason for number 1? The process is asking for operating system to provide some data, or process is asking for operating system to put it in a block state, like sleep, right? I can do that too. Okay, but if the process is not running, how could this happen? How could a not running process ask for the operating system help, or how could it do anything, right? So there is no way that I can do that. Okay, I can do that. I mean, there is no way that number 1, the transition number 1 can happen with the ready status. Okay, so good.
I have a question. Is operating system going to the block state? If it is going to go to block state, who's gonna erect the operating system?
Operating system, since there is only, that's a very good question actually. Since there is only one CPU, okay, since there is only one CPU, one process can use that CPU. It is either a regular process or the operating system, okay? All the other processes, either they are blocked or ready, right? So operating system is always ready to run, because if somebody is asking operating system to help, operating system responds, right? So operating system is waiting in the special ready state. So whenever this number one happens or number two happens, okay, operating system is doing that. Operating system is answering either a system call, or operating system is handling some kind of an interrupt. So you are saying that who is going to put the operating system from ready state to the running state? It is either a system call from a process or an interrupt that happens by a hardware component. Okay, so these states are not exactly valid for the operating system. Operating system never goes into the ready queue. Okay, operating system doesn't go into the ready queue, but part of the operating system could be in the ready queue. For example, backup services. Somebody is taking a backup of the whole operating system. It's a process, right? It is taking a backup. So it could be waiting in the ready queue, and whenever the CPU is available, this is going to be used. It is going to be running the program using the CPU, and time is up, it will be interrupted and it will be put in the ready queue again. Okay, so many processes that I showed you here are parts of operating system. In monolithic systems, there is one single operating system, but in the others, there are many stuff. This one is waiting for something to happen. Okay, it is blocked. So these kind of special operating system processes could be in the ready queue or the block queue.
Can I have a question?
Sure.
Is there any difference the transition in kernel mode or user mode? I mean, if the process is running in kernel mode, is it different the transition?
No, well, this picture doesn't say anything about it, and there is no difference between them now.
Okay.
Okay, but usually when you do the transition from the user mode to kernel mode, that means that there is a system call happened or there is an interrupt happened. Okay, so many of these processes, they run in the user mode and they ask the operating system to handle something for them. Okay, so they are doing the operating system calls too. Good. Any other questions? Any other questions? No? Okay, then I will continue. So this is process states. We understand them. So if you understand them, you kind of know what a basic process is and the relationship between the operating system and the processes. Yes?
So, every in that picture, every transition, every number means there is a context switch, right? Running to block, running to ready, ready to running.
Well,
Everyone it means that there is a context switch process.
context switch is this. Somebody was using the CPU. Now that process is not using the CPU, somebody else is going to use it. So I need to change the context. I need to change all the registers, back up the old register values, load the new register values, and for the virtual memory there are very large tables to be updated, and your cache usually is invalidated because the data for your cache is not valid anymore. That's the meaning of context switch. So if the CPU is changing hands, that means context switch. Okay, so if a process is going from running to blocked, definitely somebody else is going to use the CPU. There is a context switch. So all of the other than number 4, with the number 4, okay, with the number 4, a process is blocked. Now it is ready. That process is not going to use the CPU right now. Okay, it is in the ready queue. But when I do this, after doing this, of course, operating system has to choose, a scheduler has to choose a ready process from the ready queue, and then context switch is going to happen.
Okay, thank you.
Okay, operating systems are okay. Let's look at this one. A running program is asking for something. Is asking an operating system. Running program is asking operating system to do something. Operating system takes the call, and operating system realizes that the data is ready. It just hands over the data to the. It just hands over the data to the original process, and the original process can go on now. Can go on. It is the decision of the operating system to make that process into the ready queue, or let it use the CPU again. Okay, if it lets the original process use the CPU again, the cost of the context switch is smaller because it didn't go to anywhere else. An operating system can make these kind of optimizations. Okay, so the context switch has two costs: switching from process to operating system, then operating system to the another process. Okay, but if I am going to the operating system and coming back again, the operating system might be optimized to handle this in a better way. Okay, good.
Okay, so thank you.
Okay, the process states at the bottom of my operating system, lowest level on top of the hardware, I have my scheduler. Scheduler is one of the most important parts of the operating system itself. As the name implies, it schedules the processes. It decides which process should be running, which processes should be waiting in the ready queue. So lowest layer of the process structured operating system. Okay, it handles the interrupts and it handles the scheduling. Okay, on top of it, we have our processes running. Okay, and as we said before, none of those processes know anything about the scheduling. None of them says that it is my turn to use the CPU now. None of them says that I am waiting for an interrupt to happen. Okay, all of these stuff is handled by the operating system. That's the idea of abstraction of the CPU. That's the idea of processes. Okay, and the scheduler makes it possible. The scheduler is not that complex. Usually some assembly code is involved. Okay, and I need to make this simple because it runs so frequently, and it has to run very, very efficiently. Okay, so don't make it too complex, otherwise it will take too much CPU and time and memory space. Okay, that's the scheduler. So we keep talking about processes. Operating system knows lots about the processes. It keeps the process information in a special table, okay, called process table. Process table is the data structure that keeps all the information about the processes, so operating system can make decisions on them, can store process related information on that table. So let's look at this table that lists many possible information about each process. So let's say this is process number n. Operating system keeps all that information, process number n, whether it is running ready or blocked. Okay, so the process management, it keeps all the copies of registers of the blocked and the ready, of the blocked and the ready processes. Why? Because when a ready process when the ready process uses the CPU, I have to load all the register data to the real registers so that that process can run. Again, special registers, program counter, PSW, stack pointer. Process state is again is in there. Whether it is running, it is blocked, or it is ready. Okay. Priority of the process: high priority, low priority, medium level priority. Scheduling parameters. What do I mean by scheduling parameters? For some algorithms to run, they need parameters. For example, when this process is created, the scheduler say that this process is going to use 50 milliseconds of CPU time at a time. Those kind of parameters we are going to see will be available. Of course, the process ID, PID, process ID, process group, the users of that process, the signals for the Unix operating system. Okay, that means that what kind of signals can I handle? The kill signal, interrupt signal, suspend signal, stop signal, etc. Okay. Time when the process started. Why is this important? Time when process started, CPU time used by the process, children's CPU time.
Maybe to decide there is enough time that has been used by these processes or not.
Yeah, definitely for the scheduling purposes. If this process has used too much CPU time, maybe I will put this process at the end of the ready queue. Okay. If it is at the ready queue, at the end of the ready queue, it's going to take some time for this process to use the CPU again. Okay. Another one is time of the next alarm. Okay. I am in a block state. Okay, I am waiting for the timer to happen. Let's say I issued this one. I set the operating system that I am going to sleep for 100 milliseconds. So my alarm is set. In 100 milliseconds, they will wake me up. So operating system knows this information by looking at this one. I am in block state until this time passes. Okay. And then since I am a process, okay, I have my memory configuration, remember? I have my text, data, and stack, right? So my text pointer, data pointer, stack pointer, and this area is empty. So I need to keep pointers for those, okay, where they are. And it could be more complicated than just 3 pointers, okay? The starting address, end address, and etc. So I keep all that information in my memory management section of the process table. And then file management. I need my root directory. Where is my root directory? Where is my working directory? My open files, their file descriptors, okay? My user ID, my group ID for Unix systems, and etc. So many things that are related to the processes are kept in this table, and this table is very long. See you have seen my processor, right? There are 200 of them. So each one will carry this kind of information depending system to system. There would be more, there would be less. Okay, and again, what was the definition of a process? A program in execution. You don't have any of these information for a program. You don't have this information for a program sitting on the desk, right? Your A.out doesn't have any of these information. But when your program starts running, it becomes a process, and all of this information has to be there, and operating system keeps it. Murat has a question, I guess. Murat, do you have a question?
I think you answered it. Is all of this information on main memory or on disk? I think it's main memory.
It has to be in the memory, otherwise it would be too slow because switching has to happen very fast.
It's too much for a process. We can 200 processes, and it will consume main memory too much.
If each one takes 1 kilobyte of data, 200 kilobytes is not that much, considering nowadays we have 8 gigabytes of memory available. Right? So if I have 8 gigabytes of memory available, how much memory do you think Windows uses? At least 2 gig, right?
Yeah.
I mean, if you have a computer with 4 gigabytes of memory, your computer becomes very slow, right? If you load up 2 or 3 programs at the same time.
Sir, here is... go.
And can I ask you a question? When our process, for example, makes a call sleep 100 milliseconds, does the operating system guarantee that time is 100 milliseconds? For example, during that 100 milliseconds, it will let other processes to run, but it should stop them at the end of 100 milliseconds. When we say in our program sleep 100 milliseconds, is it really 100 milliseconds?
No, it is not. It guarantees that you are going to wait at least 100 milliseconds, but it could be more.
Okay.
Because usually our regular operating Windows is not a real-time operating system. Okay, time is subject to the other tasks that needs to be run. Okay, nobody is going to stop some other process because an equally created process needs the CPU right now, unless the priority is higher. Even if you have that, the regular operating systems, not real-time operating systems, do not guarantee anything about the time. When I ask the operating system to do something for me, read some data from the disk, it could be back in 100 milliseconds or 5 seconds. Nobody would know. No guarantees.
Thank
you.
Sir, I was about to ask if all of these information can be used as something to detect processes. So you said like detect malicious processes. So you asked like why all of this information is stored. Couldn't this be used to detect malice in running?
Well, of course you could, but this is not a. These are regular information. How could you say that this is a process with bad intentions by looking at this metadata? Usually, to try to understand if a process is a process with bad intentions, you need to check its code, analyze the code that is executing.
Well, from the behavior, from the resources, from what kind of children it spawns and stuff like that.
Well, it could be useful, but that would be too. That would be a too general information. You need more specific information.
All right. Thanks.
Okay.
But there is also a parent process information. When it can be used for which purposes? Parent process information.
Yasin, I really did not understand your question. Could you speak louder?
There is also parent process information.
Yes.
On which stuff the scheduler or the operating system will use the parent process information?
Okay, you mean this parent process. Remember, for some systems like Unix-like systems, there is this process hierarchy. Okay, there is a process hierarchy. If I kill the parent process, all the child processes will be killed too. So you need this relationship.
No, sir. If you kill the parent, the child process, the init process inherits the child process.
Though, I mean, depending on the system, those kind of stuff will be done. And for some systems, when the CPU scheduling is done, some schedulers say that, okay, I am going to look at how much CPU you used. Also, I am going to look at how much CPU your children has used. Okay, so that people wouldn't fork lots of children and let them do their jobs for themselves. Okay, because those are all the process of yourself, and if you have too many children, okay, then all of you are consuming CPU and memory. I won't let that happen. Okay, let me move on. You remember this picture, the interrupt handling. Whenever an interrupt happens, the hardware says that, okay, I'm going to stop the current process. I will trap to the kernel. Now I am at the kernel, and the kernel takes the interrupt number, and it finds the appropriate interrupt handler. It executes it, and then scheduler activates the next process to use the CPU. Okay, this is what I have shown you before. Now let's look at more details of this interrupt handling. Okay, skeleton of what the lowest level of operating system does when an interrupt occurs. Okay, suppose we have a user program, a process is running, a disk interrupt happens. That means that the data is ready, and I put my data. The controller says that, okay, I put the data in my controller buffer, so somebody has to take this data from my controller buffer and has to transfer it to the system memory. Okay, so as soon as the interrupt happens, the hardware, not the software, okay, not the software. So this number 1 and number 2 is done by the hardware. This part, hardware. Operating system did not come into the picture, but we need to know what the hardware does. So hardware stores the program counter, okay, program status word, and important registers into stack, so that we know where we left in our current process. And then hardware loads new program counter and the necessary registers from the interrupt vector. Interrupt vector is somewhere here in the kernel, okay, in the special memory. So it is all the hardware does. The operating system did not do anything yet. So since the hardware loaded new program counter and necessary registers, okay, the execution starts at a new place and in the kernel mode. Now I am executing a special assembly language procedure determined by the operating system. There is a question here, okay? The hardware doesn't store all the registers. It only stores some special registers only. Why do you think so? Why doesn't the hardware, the CPU, save all the registers to the stack?
Those registers might not be used by that process. They might be used by operating system, maybe.
No, well, I cannot know what kind of registers the processes are using. I mean, remember, for 32-bit CPUs, there are 32 registers available, and processes are free to use all of them.
Maybe since other registers can be callable from cache or main memory, I mean, they have not effect on running of the process. So maybe
No, that's not it. No. Let's read number 3. Maybe you'll understand from there. Now assembly language procedure started running. Now operating system is running something, okay? So that the assembly language procedure initiated by the hardware starts running, and it says rest of the registers. Do you know why now? Why doesn't the hardware save all the registers? The hardware saves only the minimal registers. Okay, without saving the program counter or the program status word, I cannot go back, I know that. But if I am not going to, as hardware, if I am not going to use any of those 32 registers, then I don't need to save them. Maybe the operating system is not going to handle anything. It will just return back, right? In that case, there is no need to save all the registers. But in our case, operating system started running with the assembly language procedure. It saves all the registers now to a special place. Okay. All interrupts start by saving the registers, often in the process table right here. Remember process table registers? So I know that the process 1 was running, an interrupt happened. The hardware saved a few registers. The rest of them are saved by the assembly language procedures. Okay, and I keep them on my process table. Okay, and then assembly language says that I am doing the context switch now. Okay, I need a new stack because interrupt handler is going to work now. Okay, and I need new sets of registers and everything. I save everything, and now my real interrupt handler is ready to work. That interrupt handler is usually written in C, high level language. Okay, it is written in C, and whatever it does, remember the original interrupt as disk interrupt. Whatever it does is related to the interrupt happened. So that C interrupt runs, it lets the driver to load all that data from the controls buffer to the memory buffer. Okay, what is the memory buffer? Where do you think that all that data going to the memory? What is the address of the buffer in the memory where this data is going? The controller knows where the data is now because it is in the controller's memory. But I need to transfer all that data from the controller's memory to the main memory. So what is the address of the main memory buffer? Where am I copying all that data?
The current stack, maybe?
Current stack? No. Well, it could be in the current stack, but I need some space, right? I cannot overwrite the current stacks already use values.
Maybe heap.
But where in the heap? Where in the stack? You need to tell me the address. Where is the address?
I think only the operating system can know this information.
No, we could know that too. Because operating system did not initiate this disk reading by itself. Somebody has asked it, right?
Maybe there is a special pointer which is 0, and then we add the number of the process. So process ID.
No. You are missing the point. Why do I need that information from hard disk? Because somebody said that read from this file descriptor, okay, to this buffer 100 bytes, right? So the operating system, this is a system call. Operating system knows where to write all that data to this buffer. I already sent the operating system where to put all that data. Okay, it is not in there, but you remember that read system call, right? Okay, so operating system knows where to put all that data. So this C interrupt service reads the data from the controller's buffer and puts it into the buffer that I have already set as parameter to the system call. Okay. This number 5 is written in C, but I cannot do number 3 or number 4 in C, because I like to do everything in C because it is convenient to write, easy to debug in C. But 3 or 4 has to be done in assembly, because there is no way that I can issue C statements to save registers, set up new stacks. Okay, C doesn't do that kind of stuff. Okay, C runs low-level code, but C is not that low level to change the values of the registers, save them, change the stack register, and etc. Okay, those are assembly level stuff. And after interrupt service routine runs, okay, which is determined by this assembly language stuff, okay, then operating system initiates the scheduler, tells that, okay, pick a process from the ready queue so that I can run it. By the way, in number 5, since the data is ready now, the operating system can put a process from the block state to the ready state because the data is ready. And the scheduler decides which process to run next. And the C procedure returns to the assembly code. And again, assembly code loads up all the registers and memory from the process table of the process that's going to use the CPU, because scheduler already has decided which process is going to use the CPU. And after that, all the registers are set up, and I return from this interrupt process. Some other process or the same process is using the CPU. Okay, this is how we implement the interrupt handling. Interrupt handling is handled by the operating system from 3 to 7. Okay, maybe some part of L8. Then we definitely need help from the hardware to interrupt the running process and to save some data while the process is running. Okay, any questions on this set of steps?
Did we answer the question where the data is going? I didn't catch it.
We are handling an interrupt request, right, from the disk. Why would the disk produce an interrupt? Because it is reading some data from the disk, and the data is ready, right? Why is it reading the data? Because somebody has issued this system call, read from this file to this buffer 100 bytes, right? So
Yeah.
disk is trying to satisfy this request. When the data is ready, somebody has to transfer that 100 bytes from the controller's buffer to the buffer of the process that it needs the data. Okay, so this C interrupt service transfers all that data from the controller's buffer to the process's buffer. Okay? Any other questions?
Sir, I didn't quite get number 1. I didn't quite get why we don't save all registers. So in number 3, we said that assembly language procedure saves registers. From what I understand, it means something like call conventions, I guess. I'm not sure if I understand correctly though.
Well, hardware doesn't know about your operating system. Hardware doesn't know about your process table. Number 3 saves all the registers, everything in your process table in the appropriate places. Hardware doesn't know anything about hardware doesn't know much about your operating system. So hardware says minimal number of data to some stack, okay, and then lets the operating system to handle the rest. Okay, So hardware doesn't try to do much. It says that saving the program counter, program status word, and all important registers so that assembly can start running without affecting the program interrupted. Now assembly knows that the program counter was saved, program status word was saved. I'm going to save them to the process table anyway, but I am going to save all the others. While assembly language process is doing this, it is very careful not to modify unsaved registers, right? But assembly language couldn't do anything without modifying the program status word or program counter. But I know that those are already saved by the hardware.
So operating system, when context switching, operating system doesn't store all the registers, or am I wrong about this?
No, it stores all the registers. Hardware doesn't store all the registers.
Oh, okay, now I get it. Okay.
Okay. So hardware is something that you have learned last semester from the architecture course, right? You know what happens with the hardware when the interrupt happens. You know how to handle an interrupt. You know when if there is more than one interrupt happens, how to handle multiple interrupts, one interrupt waits and etc. Okay? You know that much. We are trying to do more here. If hardware does that kind of stuff, how am I going to run the rest? So the rest of them is handled by the operating system. We cannot do we cannot do handling of the interrupts without the hardware's help. Okay, interrupt means hardware. So I should know how much hardware does for me. So what does the hardware do? It says that okay, program counter, I am going to save you. Status word, I am going to save you. Now I am going to modify the program counter so that it runs this assembly language procedure. Okay, but that's it. After that, now operating system has the control because that assembly language procedure is written by the operating system designer.
The OS also has all these steps or different?
Who has these steps? The OS? All the OS, you mean all type of operating systems? Ebru, I did not understand your question.
The OS also is a process, right? So for example, interrupt happens, is it all works this way?
Yeah. You are saying that when the operating system is running, when the operating system is doing something, if an interrupt happens, yes, exactly. When the interrupts happens, if the operating system is running, then all these steps happen again, unless operating system disabled the interrupts, because for some critical sections, operating system has to disable all the interrupts, and in that case, I cannot take any interrupts. Okay, and we are going to see at what conditions we disable the interrupts. Yes, Usama. Usama, you have a question?
All right. Yeah, I was muted. Sorry. So, first thing, in architecture, I don't remember that we have covered interrupts. So I may be a little bit back, but I want to paraphrase what I understood, and you tell me if that's correct. So there is something called the interrupt vector that is stored in the hardware somewhere. The hardware backs up some registers that are critical and puts the interrupt vector instead of it, so that assembly language using the data in these registers can run to back up the rest of the registers, handle everything. Then like C handles the interrupt itself, gives it back to assembly language to restore the registers, and then the assembly language gives the hardware a node so it also can restore the rest of the registers, right?
Well, actually, yes, that's correct. When you return back from this one, all you do is just then execute a return statement, and that return statement means that load the program counter, from stack. So everything is set
I
up
see.
by the assembly.
I see. All right, thanks.
Okay, but I think you are mistaken that they didn't teach you how to handle the interrupts with the hardware. You should have learned it in one of your courses. Can anybody help? Where did you learn it? Silence. Okay, learn how to handle the interrupts with your hardware and come back next week, okay? I am out of time for this week, and we are going to continue our discussion next week. That's it for this week then.
All right. Have a good day, sir.
You too. Bye.
Thank you, sir.
Thank you.